Hi class, we are now going to cover resonance in 10.6. So resonance, molecules of a polyatomic ion or molecules which have two or more Lewis structures with the same arrangements of atoms are needed to describe the bonding that is happening. So let me break this down. There are some compounds that one drawing, a Lewis structure, does not work. It actually has other things going on, and that's why we have to draw out the same structure. But if you notice, what's happening here is that the double bond moves, and it moves for the amount of oxygens that you have here. If we're looking at this is carbonate. So we have to draw all the structures out to show that there are other structures happening, showing this electron dispersion going on here. This is what a resonance structure is called. So we use these double-ended arrows to show this, and you keep the charge throughout, or you can do one big thing here. I can show you that. So what it is that these structures don't change. If you notice, the compound itself, it stays the same. So we don't move the compound. What is moving is the electrons. So this double bond then goes to a single bond, and you see that it moves around. So the electrons are moving around. The structure is staying the same. But when they have found in nature, some compounds do have one structure. They don't have three structures. What we're showing here is a drawing of an average of these structures. So the actual structure is an average of this, but this is the best way for us to show this, because we can't draw one, it's inaccurate, and we can't draw two, it's still inaccurate. We have to draw the three for this compound. The bond lengths are identical, and between those is single and double bonds. So that is this is what resonance is drawing more than one structure to indicate how a molecule is actually, the electron density is they call it delocalized, and that's just how it's spread out. Okay, so let's take a look at an example. So when writing Lewis structures to some molecules, for instance SO2, we can write more than one. So here we have two oxygens and one sulfur, and we put the sulfur in the middle. So if you have one, remember we try to keep this as symmetrical as possible. We add up all the electrons and we start adding them in. So what we end up having is a double bond on one and a single bond on the other. But here's something that, now there are other resonance structures that don't involve oxygen, but what I'm going to say matches for oxygen. The number of oxygen molecules that you have usually tells you how many structures you have to draw. So in this case, there are two oxygens, so you need to draw this with another drawing besides this one to indicate the other resonance structure, because it's got to look symmetrical. So in this case, it's showing a double bond on this side. We need to draw a double bond on this side and put them together. So the two structures are equally correct. We find that the molecule exists in nature as an average or intermediate of the two. So that's why we can't draw one alone, because it's not correct. So here it is, and we would draw them both. So you see there's a double bond here, but then on the other side it moves here. Nothing else changes. The actual structure does not change. If you change the structure, it is no longer the compound that we are working with. So again, a double-headed arrow is used. It's called a resonance structure or resonance hybrid structure. The true structure of SO2 is an intermediate. This is why we draw this. Both structures need to be shown. And again, if you have oxygen, the number of oxygens that are on the outside, that tends to tell you how many structures you have to draw. So here's another one. This is nitrate. So nitrate has three oxygens, so there is three structures here. And you can draw, instead of writing this out with the charge on it, on every one, what you could do is leave the charge off, put the brackets and a charge at the end, and that means it represents all of these. So again, we try to keep this as symmetrical as possible, and what you see is this double bond move to all of them, because all the oxygens are equivalent, so they all have to represent showing a single and a double bond. All right. So the arrow does not mean the molecule flips back and forth between the structures. This is showing that there's an average between all these structures that are being shown. The bonds are neither single nor double. They are an intermediate of the two. So again, if you have, this one is a little different because it has three oxygens, but you see one is in the center. So we can't use that. I'm talking about terminal oxygens. So in this case, there would be two structures because you have to represent the fact that this is a symmetrical molecule and the double bond moves from this to this. Structure does not move. The electrons are what is moving. So when you draw these, how do you know you're dealing with the resonance structure? Well, it's not a quick, easy answer, but polyatomic ions tend to have resonance. If they have oxygens, more than one, obviously we can have two, you're going to need something that has two. So that was a dumb statement on my part. But so oxygens, terminal oxygens, is an indicator that you have more than one structure. Also, there are molecules that are not polyatomic ions, but they have to be symmetrical. So there's not really a quick and easy way. So that's why I've given you more examples so you can see some of these others that are resonance structures. But after you start drawing Lewis structures enough, you should be able to see that, okay, I'm drawing this here, but I have one that looks exactly like it on this side. This is going to be a resonance structure. I need to draw it. And that tends to usually be, if you see, they're all symmetrical. So if they're all symmetrical, you have to show the oxygens are all equivalent. So that's the best way I can explain it because there's really no set rules. And that's it.